In this episode, we move from protecting data sitting still to protecting data while it is moving, because many of the most valuable moments in a system's life happen when information crosses a network. Data in transit includes web traffic, remote administration sessions, application connections to databases, and the quiet background synchronization that keeps modern systems functioning. Beginners often assume that if something works over a network, it is simply working, but security asks an extra question. Who can see it? Who can change it? And how do the endpoints know they are talking to the right partner? That is where transport layer security, TLS, and certificates come in, because they create a way to encrypt traffic, prove identity, and detect tampering in a standardized manner. This is also where virtual private network, VPN, ideas show up, and WireGuard is a modern example that gets mentioned often because its design is intentionally minimal and focused. We will also connect this to hashing, because hashes are used all over modern security for integrity and verification, and we will talk about weak algorithms, because security failures often come from using outdated cryptography long after the world has moved on. The goal here is to give you a calm, beginner-friendly mental model for how TLS stacks work, what certificates really represent, what WireGuard is doing at a high level, and how hashing and algorithm choice fit into the bigger story. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A useful first step is to define what data and transit threats look like, because the controls make more sense when you can picture the attacker. One threat is eavesdropping, where someone captures traffic and reads it, which is a big risk on untrusted networks like public Wi-Fi, but can also be a risk inside organizations if networks are not segmented. Another threat is manipulation, where traffic is modified in flight, which can corrupt data or inject malicious commands. Another threat is impersonation, where an attacker tricks a client into talking to the wrong server or tricks a server into accepting a client that is not legitimate. These threats are not theoretical, because attackers use techniques like man-in-the-middle interception, rogue access points, and poisoning of name resolution to redirect traffic. If you have ever typed a password into a page and wondered if it is really the right site, you have already felt the impersonation problem. The promise of secure transport is to reduce all three threats by encrypting the traffic, validating identity, and using integrity checks so changes are detected. That promise is what TLS is designed to deliver. To understand a TLS stack, think of it as a set of coordinated components rather than a single magic box. At a high level, there is a protocol that defines how two endpoints negotiate security, how they agree on keys, and how they then protect the application data. There are cryptographic algorithms that perform functions like encryption and integrity, and there are libraries and implementations that actually run the protocol, which is why people sometimes refer to a TLS stack. There is also the certificate system that supports identity verification, which connects the cryptography to real-world names like domain names and organizations. During the initial handshake, the endpoints exchange information that lets them choose compatible settings, prove identity, and derive shared secrets. After that, the bulk traffic is protected in a way that is meant to be efficient and resistant to common attacks. For a beginner, the most important idea is that TLS has a negotiation phase and a protected data phase, and the choices made during negotiation determine how strong the protection is. Certificates are often the most confusing part for new learners because they sound like physical documents, but in practice they are digitally signed statements about identity and keys. A certificate binds a public key to an identity, such as a domain name, and it is signed by a certificate authority, CA, that the client trusts. The client verifies the signature, checks that the identity matches what it intended to reach, and checks other validity conditions, such as expiration. If all of that checks out, the client gains confidence that it is talking to the right server, because only the rightful server should have the private key that pairs with the public key in the certificate. This is a trust chain, meaning the client trusts certain root authorities, and those authorities can sign other authorities, which can sign identity certificates. Beginners do not need to memorize the entire chain building process. but they do need to understand that the trust is not automatic. It is based on a set of trusted routes and validation checks. When certificate validation is bypassed or misconfigured, impersonation becomes much easier, which is why certificate errors are serious signals, not annoyances to click through. Another key part of certificate thinking is that certificates have lifetimes and management requirements, which is why organizations pay attention to renewal and revocation. If a certificate expires, clients should treat it as invalid, because an expired certificate might indicate neglect or a potential attempt to reuse old credentials. If a private key is compromised, the certificate that binds that key to an identity becomes dangerous, because an attacker could impersonate the service. Revocation is the idea of telling clients that a certificate should no longer be trusted even if it is not expired, though in practice revocation checking can be inconsistent depending on client behavior. The exam-level understanding is that certificates are not forever, and they require lifecycle management to remain trustworthy. This also ties into why automation for certificate renewal is common, because manual processes often lead to outages or insecure workarounds. If you treat certificates as living credentials rather than as one-time setup artifacts, you will understand why systems break when certs are neglected. Hashing enters the story because secure transport is not only about secrecy, it is also about integrity, and hashes are a fundamental integrity tool. A hash function takes input data and produces a fixed-size digest that changes dramatically if the input changes even slightly. Good hash functions are designed so that it is hard to find two different inputs that produce the same digest, and it is hard to reverse the digest back into the original input. In transport security, hashes and related constructions are used to verify that handshake messages have not been altered and to support message authentication, which helps detect tampering. Hashes are also used outside of TLS for things like storing password verifiers and checking file integrity. But here the important link is that hashing helps ensure you are receiving what was sent. A beginner pitfall is to confuse hashing with encryption, because both involve math and both produce unreadable-looking outputs. Encryption is meant to be reversible with a key, while hashing is meant to be one-way and used for comparison and verification. The topic of weak algorithms matters because cryptography is not static, and what was considered strong 10 or 20 years ago may no longer be safe today. Weak algorithms can include old ciphers, short key sizes, or hash functions with known collision weaknesses, and attackers can exploit those weaknesses to decrypt traffic, forge integrity checks, or impersonate identities. The reason this shows up in exam content is that security professionals must recognize that using cryptography is not enough if you use broken or outdated cryptography. A system might claim to use TLS, but if it negotiates weak cipher suites or supports obsolete protocol versions, the protection may be far less than expected. This is why secure configurations often disable old protocols and restrict negotiated options to modern, vetted choices. The beginner mindset here is to treat algorithm choice like choosing a lock, where some locks are known to be easy to pick, and using them is worse than it looks because attackers already have tools and experience against them. Now we can introduce WireGuard as an example of data-in-transit protection with a different purpose than TLS. Where TLS often secures a specific application session, like a browser to a web server, WireGuard is used to build a secure tunnel that makes two networks or two endpoints behave as if they are connected through a private link. WireGuard is designed with a smaller, simpler configuration model compared to some older VPN approaches, and it relies on modern cryptographic choices with an emphasis on a clean, minimal design. At a conceptual level, WireGuard uses public key cryptography to identify peers and establish shared secrets, and then it encrypts traffic flowing through the tunnel so outsiders cannot read or modify it. It is also designed to be efficient, which makes it attractive in environments where performance and simplicity matter. For Linux Plus learners, the key is not deep implementation details, but understanding that WireGuard provides encrypted tunneling, that it has a concept of peers, and that it uses keys to define who is allowed to connect. It is useful to contrast the identity models in TLS and WireGuard because it clarifies why certificates show up in one and keys show up in the other. In typical web-focused TLS, identity is often expressed through certificates tied to domain names and validated through a CA trust chain. That makes sense for the internet, where clients need a scalable way to trust many services they have never met before. In WireGuard, identity is often expressed through static public keys for peers, where the administrator controls which keys are trusted, which fits a VPN model where participants are known and managed. Both are forms of public key cryptography, but they serve different operational models. Beginners sometimes assume certificates are required for all encryption, but certificates are one way of packaging trust, not the only way. Understanding that difference helps you answer exam questions that ask you to choose an appropriate approach for a given scenario, like securing a public website versus connecting two private networks. Another important link is that data in transit security often depends on proper verification, not just on turning on encryption. If a client does not validate the server certificate correctly, it may encrypt traffic to an attacker, which defeats the purpose of authentication. If a VPN peer trust list is too broad or keys are mishandled, unauthorized peers might join and observe or inject traffic. If weak algorithms are allowed, attackers might downgrade or exploit the negotiated settings. This is why modern security thinking emphasizes secure defaults, strict validation, and reduced optionality, because optionality is often where mistakes happen. For a beginner, the message is that secure transport is a system, not a checkbox, and it requires that identity checks, key handling, and algorithm choices all align. When those pieces align, the result is strong protection against eavesdropping and tampering. When they do not align, you can end up with encryption that looks present but does not provide the security you assumed. There is also a practical angle to troubleshooting that does not require typing anything, which is to interpret symptoms as belonging to one of a few common categories. If a client refuses to connect due to certificate issues, the problem might be that the certificate is expired, the name does not match, the chain is not trusted, or the system clock is wrong, because time matters for validation. If a connection works sometimes and fails sometimes, the issue might be renegotiation, load balancing with inconsistent certificates, or mismatched configuration across servers. If older clients cannot connect after an upgrade, it might be because weak protocol versions or weak algorithms were disabled, which is often a security improvement that needs a compatibility plan. For VPN-style tunneling, failures often relate to key mismatches, peer authorization, or network paths that block the tunnel traffic. The important beginner lesson is that many secure transport failures are actually validation failures, and validation failures are often deliberate, meaning the system is refusing to proceed because it cannot prove identity or cannot negotiate safe settings. By connecting all of these ideas, you can see a coherent picture of data and transit security that explains why certificates, hashing, and algorithm choices matter. TLS stacks provide encryption and integrity for application traffic and use certificates and trust chains to authenticate identities at scale, especially for public services. WireGuard provides encrypted tunneling for controlled sets of peers, relying on key-based peer identity rather than public certificate chains in the common use case. Hashing supports integrity and verification, and it is distinct from encryption even though both are central to modern security. Weak algorithms and obsolete protocol options are dangerous because they allow attackers to exploit known weaknesses or force weaker negotiations. So secure systems limit what can be negotiated and prefer modern choices. When you can explain these concepts clearly, you are prepared to reason about why encrypted traffic is trustworthy, what breaks when certificates go wrong, and why algorithm hygiene is not optional. That reasoning is what Linux Plus expects, and it is also what helps you build and evaluate secure systems in the real world.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.